Hello once again, AP Calculus BC students. Mr. Record here from Avon High School, and we are going to be continuing our discussion on Taylor and Maclaurin series in the Larson textbook, section 9.10. And our main focus today is upon the function f of x equaling 1 plus x to the k power, which is a general form for your binomial series. Larson, as well as many other authors, consider this to be one of the basic series that would typically appear in your basic list. But we're going to go ahead and just kind of step back and let the k be some arbitrary constant, and we are going to expand this and see what the series looks like. Because we don't really have any prior knowledge about, the behavior of 1 plus x to the k, we are going to go ahead and expand it out the rigorous way by taking several derivatives. All right, and then hopefully you can apply some of your knowledge from perhaps your algebra class to start seeing some patterns. So, very first thing we're going to do, I'm going to just recopy the f of x function here. F of x would be, of course, 1 plus x to the k power. Let's take several derivatives. First derivative, f prime of x. Well, the k would pop out to the front, and we would then have our 1 plus x raised to a power less than k, or k minus 1. And technically, we would be obligated to use the chain rule here. We would have to take the derivative of this 1 plus x term, but because the derivative of that is 1 and will continue to be 1 throughout this problem, we don't have any other sort of significant change to our derivative. Second derivative. Well, the k that's already out in front will be joined by a k minus 1. And now our 1 plus x would be, of course, raised to the k minus 2 power. All right, let's go ahead and take a third derivative. And at this point, it's pretty easy to start to pick up on the pattern. We, of course, would have k times k minus 1, now times k minus 2, times the quantity 1 plus x times k minus 3. Now, it can get very tedious to take more derivatives. So maybe now we are in a position where we could figure out what sort of a formula would be for any nth derivative. Well, let's take a look. Well, what do we notice? Well, we're going to see these factors of k, starting with k and k minus 1 and k minus 2, continually to build. They're not going to go away. The question is, where would they stop? What would be the final k expression prior to getting to the binomial piece here that has the x in it? Well, if you just do a little bit of comparison, and I'll switch, tell you what, I'll switch colors here for emphasis. If you compare, let's say in the third derivative, what kind of constant that you had in that binomial, k minus 2, with the derivative that you took, in this case the third, you'll notice that it is 1 less. And that pattern actually does proliferate through the rest of the problem, both prior to the third derivative and after the third derivative. So for that very reason then, it's probably likely that your final k expression would be k minus one thing less than n, 1 less than n, which would be the quantity n minus 1. Well, if this is k minus the quantity n minus 1, then I could go ahead and distribute that negative, clean this up just a little bit, and I would have k minus n plus 1. So maybe up above here, I'll just kind of emphasize the fact that this was born out of that expression there. Okay, and then for the very final component, that would be your binomial 1 plus x, and then we have to carefully consider, what exponent are we going to be talking about here? Well, once again, if I'll switch colors and we'll compare, here the exponent and by here I mean in this term, the k minus 3 exponent has a very nice connection to the fact that I took the third derivative. Just as this k minus 2 exponent here has a very nice connection to the second derivative. So the 1 plus x would certainly be raised to, hopefully you can all tell, the k minus n power. Well, great. There's our derivatives. Now what do we get to do? Well, at this point, we have to take each of these functions and evaluate them the value for x that we are centered. So if we read back into the problem, see where are we centered? Well, it says find the Maclaurin series. So that means that we're centered at 0, which actually is a good thing because it's going to make the problem a little bit easier to compute here. So we've got to figure out what is f of 0. Well, f of 0, if we turn your attention over here, would be 1 plus 0 to the k power, or 1 to the k, which is going to give you 1. 1 to any power is always going to be 1. That's going to be a very common thing that we see throughout the rest of this evaluation. F prime of 0, well, that would be k, all right, we're looking over here now, k times 1 plus 0 to the k minus 1 power, which is just going to be k times 1, or k. F double prime of 0. F double prime of 0, well, you probably guessed it, k times k minus 1 times 1. So we've got 3 terms listed. It's probably going to be very intuitive that your f triple prime of 0 is just going to build upon this notion. And perhaps or perhaps not, it would be obvious from your nth derivative what's going to happen. Well, you would still have your k and your k minus 1 and your k minus 2. Now remember, we're going to let the x become 0, which essentially will wipe away this last term altogether, making it 1 to some exponent, which of course is 1, but we would still have this term involved, which would be a k minus n plus 1. So I'll use the little dot, dot, dots to indicate there are several terms in between. Now we get to put it all together. And in case you're following along with this video at home, I would suggest that you perhaps write small here in this next step. So what we're going to do, I'm going to switch to a new page so that I guess we'll have a fresh start here. We're going to throw everything together. So we'll say, let's switch back to blue. So all of the work that we have done up to this point, I meant to say which produces, all of this work will produce the following. F of 0 would be our first term, which is 1. Okay, according to our Taylor series formula, the next term is f prime of 0, right, which is our k, multiplied by x to the first, all divided by 1 factorial. Now you'll notice that I didn't write that extraneous information because it would just simplify away to be 1, the denominator would simplify to be 1 anyway. So we would just have k times x. All right. Once again, if you are having trouble following along with what the Taylor series polynomial here, or the Taylor expression is going to look like, you can go ahead and refer to some notes that you have about Taylor series in general. Our next term would consist of our f double prime of 0, which has a little bit more to it. It's got a k times a k minus 1. And then we would multiply that by x. Now remember, this is a Maclaurin series, so there is no x minus c per se. X minus 0 is what we're dealing with. That would be raised to the third. And we would divide now by, oops, I made a mistake, didn't I? We need to get this 3 out of the picture completely. This is to the second power. to the second power over 2 factorial. Remember, my counting goes 0, 1, 2. Next term, k multiplied by k minus 1 multiplied by k minus 2 x cubed over 3 factorial. I'm going to go ahead and say, let's write one more term. I'm going to write one more term down. And that term would, of course, be k minus 1, k minus 2, k minus 3. Oh, goodness, am I going to make it x to the 4th all over 4 factorial. Aren't you glad I said to write small? All right, now, this would be, I guess, 4 terms, and honestly, I probably ought to continue. I didn't have enough room on the right side, but we do know that this is a series that would go on forever. We're going to go ahead and leave it like this for the time being. But the directions to this problem do ask us to find something else, if I'm not mistaken. So I'm going to run back and we're going to take a look at that. And it says, go ahead and find the Maclaurin series. And of course, the series that we wrote is more of a term-by-term series. And I can adjust that here in just a moment, and I will. But we are also asked to find the radius of convergence. So we do have a second kind of a directive here. So if we get back to our result here, we realize then that whatever we choose to write here for the nth term, if we were to put a summation symbol in front of that, then that could be our power series representation. So let's go ahead and do just that. And we could say that we'd have the summation as n goes from 0 to infinity of, well, remember, we already computed our nth derivative of f evaluated 0. That consisted of all those crazy k terms that kept going on and on and on up until you got to k minus n plus 1, I believe, after we simplified. And then we would have our x to the nth all over n factorial. So that would be your binomial series representation as a power series. Okay, now what we're going to do is give this interval of convergence some thought. And if you think back, and I've got my class here live, and I'm going to ask them, I'm going to put them on the spot. I'm going to ask them, if you're going to find the interval of convergence for a seemingly complex series such as this, what's your technique that you want to use? Ratio test. See, they're so good. They are so good. I got them trained so well. Ratio test is what we're going to use. And the ratio test is not going to be as bad as you might think in this particular problem. We might have to write some terms out, but we'll see what happens. So if we're going to use the ratio test, let me switch colors here to kind of let this stand out a little bit. Tomorrow is St. Patrick's Day, so let's use green. So we're going to take a look at the limit as n approaches infinity. And if you recall, the ratio test, for those of you who may have forgotten, is just a matter of comparing the nth plus 1 term with the nth term by writing them as a ratio and putting them in absolute values. And our goal is for this particular limit to be less than 1 in order to be convergent. So for this particular problem, that particular limit would look like what? Well, we simply need to go in and replace all of our n's with n plus 1. So you'll notice that initially these values of k will stay exactly as they are. But, whoops, not exactly like that though, because I just noticed I came across an n value. This n value right up here, and I'm going to kind of refer back to our previous answer, If that n were an n plus 1, I would be subtracting a quantity n plus 1, which would give me a k minus n minus 1, and then of course I have the final plus 1 that you see here. So that's just going to simplify to be k minus n. Does anybody get that? And then of course I have x to the n plus 1. I'm going to go ahead and get rid of this little step here so we don't get confused. And then the denominator is n plus 1 factorial. Okay, everything look good? I'm going to ask my class. I didn't make any mistakes yet, so we can continue on. Okay, so we're going to multiply by the reciprocal, right? Instead of dividing by a sub n, we'll just multiply by the reciprocal of a sub n, which is, in essence, our original expression here. N factorial now being on top, and then the whole lot of these terms, k minus 1 I meant to say, in the denominator here. Wow, that's a pretty large limit that we're going to have to take. Well, hopefully we can do a little bit of cancellation in this problem. Let me extend the page. And let's see what we've got. Limit as n approaches infinity. Well, what will cancel? It's a great question. Well, when we look at this, we will notice initially that the k's would cancel, the k minus 1s, the k minus 2s. Seems like that's going to progress quite nicely. Now, when we get to these second to last terms, the k minus n and k minus n plus 1, we're going to have to think about that a little bit more cleverly. And the thing that you want to do is probably focus on this k minus n plus 1 and remember how he was originally written as k minus the quantity n minus 1. And to be honest, it probably would have been better off if I would have presented it like that anyway. But if you see k minus n in the numerator and k minus the previous term, the term that came just prior to n, you would notice that this whole term here, or here, would cancel with the term that came just before the k minus n. So you would be left with only, so far, a k minus n in the numerator. Hopefully that makes sense. As far as x to the n plus 1 divided by x to the n is concerned, you're going to be left with an x. And in factorial, it's highly likely that you've done a lot of simplification at this point with factorials. If not, you can find lots of resources online and on YouTube, videos on how to do that. N factorial over n plus 1 factorial is, of course, going to be n plus 1. Now, as far as sort of finishing up this limit, what we'll simply do here is I'm going to choose to separate it just a little bit. In other words, consider the k minus n over n plus 1 factor or absolute value separate from the absolute value of x, and basically do two separate limits. And what we're going to find is that the limit here, the first one, allows us to look into this and say, well, wait a minute, don't we have a shortcut that says if n approaches infinity, and we do compare the degree of n in the numerator and the denominator and find that they are the same, 1 in this case, we are allowed to just divide the coefficients. -1 on top divided by 1 on the bottom is, of course, -1. So your answer is the absolute value of -1, basically. That would be multiplied by, well, this limit here is very simple because since there's no n to approach infinity, you're just left with the absolute value of x. And of course, the absolute value of -1 is just 1. So we have x, or I'm sorry, the absolute value, I should say, of x as our limit. And if you recall, we wanted that to be less than 1. So that means that we could say our interval of convergence without testing the endpoints, so I'll put little question marks maybe around those, would be -1 to 1. But if I recall, this problem only asked for what the radius of convergence was. So the radius would just have a length of 1 if you take into consideration this entire distance being 2. So that would take care of the second part of the answer. And there you have it. There you have it. You have your power series for the general binomial series 1 plus x. And it is important to note, in this particular instance, we did refer to the value of k as being a positive integer. It changes things just a little bit, and we will get into a video later on that will take into consideration the other possibilities. So hope this helped, and we'll see you next time.